This is the first of at least 2 videos, possibly 3, that I'm going to do on inverse functions. Not every function has an inverse, but a lot of them do. The majority of the more common functions seem to be invertible. Linear functions are all invertible. And what I mean by invertible is, well, the inverse undoes what the original function does. So f of x multiplies by 3 and adds 1 in this particular case. F of x equals 3x plus 1. Again, multiplying by 3, adding 1. Well, we would undo those steps in the inverse function. So before I actually go into any more details on that, let's approach it kind of from the perspective of recognizing that you've actually been working with inverse functions ever since you start doing algebra. So consider the equation f of x equals 5. If f of x is 3x plus 1, that means that 3x plus 1 equals 5. So before I start that, just point out the obvious. Sometimes there's some confusion here. So I'm saying that y is 5, not x is 5. If x were 5, f of 5 would be 3 times 5, 15 plus 1, 16. So f of 5 is 16. What we're looking for here is what value of x would make y equal 5. Or stated differently, what's the solution set to 3x plus 1 equals 5? Well, I went through the details here. We subtract 1 from both sides of the equation, so 3x equals 4. And then 3 times x equals 4, so we undo the division, the multiplication by dividing. So we divide 4 by 3, that's the answer, 4/3. If you plug 4/3 back in the original, f of 4/3 is equal to 5. Well, there's nothing terribly earth-shattering about that. That's the algebra that you learned pretty early on. You undo these steps. You undo the adding of 1 by subtracting 1. You undo the multiplying by 3 by dividing by 3. And well, that's what the inverse function does. So back when you were first taught about solving equations, you weren't most likely taught to apply the inverse function because probably you didn't even talk about it in terms of functions. But that's really what you were doing. If we look at the expression 3x plus 1 as being a function that takes a real number and sends it to another real number, solving to get back to the number that it came from is a matter of finding the inverse, of doing the inverse operations. And often the inverse can be understood as being the inverse operations in the opposite order. What I mean by that is, well, the inverse of adding 1 is subtracting 1. The inverse of multiplying by 3 is dividing by 3. Because the original function does it in the order multiply by 3, add 1, the inverse function has to do the inverse operations in the opposite order. So first we subtract 1, then we divide by 3, as we see here. The inverse function is x minus 1, undoing the adding of 1, then divided by 3, undoing the multiplication by 3. Oh, by the way, I could actually plug 5 into this thing, and then f inverse of 5 would go to 1/3 of 5, which is 5/3 minus 1/3. 5/3 minus 1/3 is 4/3. F of 4/3 is 5. F inverse of 5 is 4/3. The function sends x to y. The inverse takes that y value, sends it back to the x that it came from. Is one way of looking at it, though we tend to always think of the inputs as x no matter what we're talking about. So it makes it a little bit different than what I just said. But look at this again. Our function f, if you were to go ahead and calculate, it's a linear function. So as x goes up by 1, the y values go up by 3 because the slope here is 3. F of 0 is 1. And then if you just count by 3s, you get the y values. The inverse function is going to be those same ordered pairs in the opposite order. If you exchange x and y, that's really what the inverse is. It exchanges these as ordered pairs. It switches the roles of x and y, working backwards. Every relation has an inverse because you can always take an ordered pair and you can exchange the ordered pairs. So as a relation, every function is a relation, and as a relation, every function has an inverse. However, the inverses of certain relations may not be functions. Once you switch the ordered pairs around, it may not satisfy the rule that says that different ordered pairs have to have different first elements. Or equivalently, that the next element has to be sent to 1 and exactly 1 y value. Okay, so let's look at a slightly more involved function here. Cube root function rather. Q of x equals the cube root of the quantity 2x plus 4 minus 7. Now it's possible to look at this function the same way I looked at the last one in terms of finding its inverse. Just reverse the order of the operations and also invert every single operation, every single individual function. So what I mean by that is it's possible to actually think of the function q as being a composite of 4 elementary functions. An elementary function is really a function that just does one little thing that can't be broken down any further. There's different ways you could write q of x as a composition. You could write it as the function that multiplies x by 2 and adds 4 and then takes the cube root. So that could be one function, and then you could have another function that just subtracts 7. So you just have 2 functions. But we can also decompose the function into a composite of 4 elementary steps multiplied by 2. So if you start at x, you multiply by 2. Then we add 4. Then take the cube root. Then subtract 7. So I label those functions as a, b, c, and d. And just think about this. If you composed b with a, remember we're starting at x, so a operates on x first, which would take 2 times x. A of x is 2x. B would then operate on the input, which is 2x. And so b of 2x is 2x plus 4. So if you just did the b circle a part of this, you would end up with 2x plus 4, which is the stuff under the radical here. I'm not going to go through the details because I think it's important that you sit down and think your way through this. Write it down would be a good idea. Convince yourself that if you take the functions a, b, c, and d, and you compose them in the opposite order, d of c of b of a, you would get the function that we have here. That's what I wrote out here. Q of x, here's the function again, cube root of the quantity 2x plus 4, that minus 7, is the composition of d with c with b with a applied at x. D circle c, circle b, circle a, applied at x. And again, you just start with a of x is 2x, b of that would be 2x plus 4, c of that would be, well, think about it, work your way through it. Now it turns out that the inverse function is going to, so each of these particular elementary functions is invertible. Not all elementary functions are invertible. The squaring function, for example, is the most simple function you could probably think of that doesn't have an inverse. The graph of the squaring function y equals x squared does not pass what's called the horizontal line test, which means that if you view the relation which makes up the function and the set of ordered pairs, the relation that makes up the y equals x squared, if you switch x and y around, the new relation will not satisfy the basic property of the function, which is that every x value corresponds to exactly one y value. So the squaring function does not have an inverse. The absolute value function does not have an inverse. It turns out that even functions cannot have inverses. None of the basic trigonometric functions that you may have run across if you have taken any trigonometry, none of those have inverses in the way that we normally talk about inverses. But all of these basic functions are invertible. What's the inverse of a of x? Well, multiplying by 2. Well, dividing by 2 is the inverse. How do you invert adding 4? How do you undo that? Well, you subtract 4. The inverse of the cube root function is the cubing function. The inverse of the subtracting 7 function is the adding 7 function. And so if you invert each of those functions and then you just reverse the order, so instead of doing D, C, B, A, which remember the order actually is from right to left here, A, then B, then C, then D. Well, if we took the inverses and changed the order, so it'd be A inverse of B inverse of C inverse of D inverse, which is what I've got written down here. Q inverse is the composition of A inverse with B inverse with C inverse with D inverse. The order is backwards of the Q function. And each of these has been replaced with its inverse, which I have written down. I already talked about these. Multiply by 2, divide by 2, add 4, subtract 4. Cube root, cubing. Not terribly exciting. That's the problem with mathematics. Sometimes it's just so simple that it's boring, and then all of a sudden it just becomes so hard out of nowhere. All those simple parts just seem to fall away, and you're left with some complicated assortment of all those simple parts. And you're missing some simple part somewhere, or some detail of how it all goes together. Anyway, if you go ahead and compose those, the inverse function, well, D inverse of x is going to be, well, that's the add 7 function. So we start with x, we add 7. Then we cube. So now we have the cube of x plus 7. Subtract 4. And then the whole thing has to be divided by 2. At each stage, what you're inputting is the previous thing. So what you would have here would be D inverse is x plus 7. Let me actually open that up and we can play around with it. So then if I took the x plus 7 and put it in place of the So I made a little change here. So D of x is x plus 7. It actually disappeared because I cut and pasted it. I should have just copied it. So D inverse of x was x plus 7. Let me put that back in there. There we go. So D inverse of x is x plus 7. C inverse would then be applied to x plus 7, which means you're going to cube x plus 7. Then that whole thing is going to be plugged in here for x, and so you subtract 4. Then that whole thing is plugged in here for x, and you end up with what we have here. It could be written with the fraction like this. More commonly, you would go ahead and probably distribute the division by 2. Dividing by 2 is the same thing as multiplying by 1/2, and then you can subtract 2 from that. You can check in a specific case to see that Q inverse and Q do what they're supposed to do relative to one another, which means whatever Q does, Q inverse undoes. So for example here, if we were to look at evaluate, I think I'll just copy that and paste it. Copy. So there's our Q function. Paste that. And I'm going to plug in 2. And so, and you could actually go along here. A of 2 is 2 times 2. B of, so which is 4. B of that would be that plus 4, which is 8. But what it comes down to is you're going to have 4 plus 4, which is 8. Cube root of 8, which is 2. 2 minus 7 is -5. I don't think we need any of that. -5. I'll talk my way through that again, see if I got that right. Okay, so 2 times 2 is 4. 4 plus 4 is 8. The cube root of 8 is positive 2. 2 minus 7 is -5. So if we evaluate Q inverse, which we have here, let me grab that real quick here, copy it. Q inverse, it's probably going to be a little bit smaller than it was, so enlarge that. Okay. So what I want to do is calculate Q inverse of -5. If these two functions are inverse of one another, they have to undo each other. So Q sent 2 to -5, Q inverse has to send -5 to 2. Well, if we look at the arithmetic here, -5 plus 7 is 2. 2 cubed is 8. 8 minus 4 is 4. 4 divided by 2 is 2. I might go over that one more time, looking at the other notation here. -5 plus 7, 2. 2 cubed, 8. 1/2 times 8, 4. 4 minus 2, 2. Now, should mention here that I didn't really prove that the two functions are inverse of one another. To really prove it, you have to do really, I guess, 4 things. You have to check that in a generic sense that Q of Q inverse of X is X, and that Q inverse of Q of X is X also. I'm going to copy that. Paste that. Okay. So what I'm saying here is that if you calculate Q of Q inverse of X is equal to X. So Q evaluated at Q inverse of X is equal to X. In other words, if you do these two functions, one after another, compose them, it's the same as if you did absolutely nothing at all. If two functions are inverse of one another, they undo each other. Or sometimes we'll talk about them being the identity function. The identity function is the very exciting function that takes a number and just says, okay, we'll keep the number just the way it is. It doesn't do anything at all. It's kind of the equivalent of 0 for addition or 1 for multiplication in terms of operations. So this is part of it. The other thing is if you switch the roles around, Q inverse of Q has to do the same thing. And so you have to show that this is generally true. And you also have to look at the two functions in terms of their domain and range. Since Q sends X to Y and Q inverse sends Y back to X, it follows from that that the range of one function has to be the same as the domain of the other function, and vice versa. So the domain of Q is the range of Q inverse. The range of Q is the domain of Q inverse. Did I say that right, or did I say the same thing twice again? The domain of one is the range of the other, and vice versa. Need to write this down so my short-term memory can remember what I did. Anyway, there's certainly more I could say about this, but I didn't want to make this video too long. So in the next case, maybe look a little bit more at the algebra of this, and also some complications that arise where it's not quite so straightforward to find this. So we'll look at a slightly different way of looking at it instead of breaking it down to a bunch of elementary functions and then undoing each one of those and doing it backwards. I think that's kind of the neatest way of doing it, but there is a more formal way of doing it. And it turns out that there are some functions where the approach I just took here won't work. So we'll take that up in the next video.